All right, so we talk about Diffie-Hellman key exchange. We talk about RSA, which was an encryption algorithm. Now we are going to talk about El-Gamal and DSA, digital signature algorithm. Actually, these are two different types of algorithms because El-Gamal is an encryption algorithm. Digital signature algorithm is a digital signature algorithm, but they are based on similar ideas. So actually, digital signature algorithm is like using El-Gamal, not for an encryption, but for digital signature. So this is why I'm going to talk both of them at the same time. El-Gamal is really simple. It depends on discrete logarithm problem. So idea is as follows. In the key generation phase, you randomly choose the secret key X, then compute G to the X, which equals to Y. So this is your secret key. This is your public key, right? So as simple as that. Okay, so instead of RSA where you need to choose prime numbers and so on, you don't deal with this. So the actual security depends on how random you chose your X. If you choose your X equals to 5, then it fails, right? Somebody can easily guess that. So encryption works like this. When you want to send message M, you randomly choose a number R. You calculate your message multiplied by Y to the R. Y is the public key that you want to communicate. Also, you calculate G to the R, which is again the generator of the group, a public parameter. So you end up with U and V. So this is the encrypted version of your message. You send it to them. And the person who wants to decrypt, since they know the private key X, they calculate the inverse of U with respect to X. So this means that actually U to the power minus X, right? So U is, remember, is this. So calculating the minus X power is, you end up with G to the minus XR. And V is M times Y to the R, and Y is G to the XR. So actually you end up with M times G to the XR times G to the minus XR, so they cancel each other. So this is why you end up with the original message M. So in this kind of algorithms, the idea is simple. When you're performing, actually, you hide your secret value X inside this parameter. So the person who encrypts do not know your secret parameter, but you use the secret parameter to get rid of these values and end up with the message M. So as simple as that. So this is for encryption. So you can use El-Gamal, but as you can see here, we are talking about the group. So you can actually choose an elliptic curve and use El-Gamal encryption there. Okay? And we will talk about elliptic curve cryptography next. So let's move on to digital signatures. A digital signature is a number dependent on some secret known only to the signer's private key, and additionally on the contents of the message being signed. Due to the size of the signatures, hash of the message is signed instead of the message itself. This is important. This is why we actually need collision resistant hash function. Okay? If your hash function is not secure, then using a secure digital signature algorithm makes no sense. Okay? Especially if you can find second primitives, then you can, forge different signatures and so on. Yes, signatures must be verifiable. This means that if a dispute arises as to whether an entity signed a document, an unbiased third party should be able to resolve the matter equitably without requiring access to the signer's private key. And actually, this is how blockchain or Bitcoin or Ethereum works, because when you transfer cryptocurrency to somebody, actually you are signing that message, saying which is the transaction, actually hash of your transaction. So you sign it, and since everybody knows your public key, they just check if your signature is correct. So all of the nodes check this, and if it is correct, then it is written to the blockchain. Disputes may arise when a signer tries to repudiate a signature it did create. So for instance, you sign the transfer of some cryptocurrency, then you deny it. But since the signature is correct, you cannot repudiate it. So when another dispute may arise when a forger makes a fraudulent claim. So you didn't sign it, but somebody has some kind of power so that they can forge fake signatures for you. So your algorithm should be secure enough to avoid forgeries. Digital signature schemes can be used to provide the following basic cryptographic services: data integrity, the assurance that the data has not been altered by unauthorized or unknown means; data origin authentication, the assurance that the source of data is as claimed; non-repudiation, the assurance that an entity cannot deny previous actions or commitments. So digital signatures provide this. A misconception: a digital signature is not an encryption algorithm. This is important because you are not trying to provide confidentiality here, right? It provides data integrity, data origin authentication, and non-repudiation. Yes, digital signature schemes are commonly used as primitives in cryptographic protocols that provide other services, including entity authentication. There are many standards for that, authenticated key transport, and authenticated key agreements. Okay, very old and new standards are here. So the most known, but currently the one that we are not going to use in today's technology, is known as digital signature algorithm, DSA, or also known as digital signature standard, DSS. But we should stop using the word standard because most probably it will be removed in all of the standards in the foreseeable future. So DSA was proposed in August 1991 by the US National Institute of Standards and Technology. It was specified in a US government Federal Information Processing Standard, FIPS, called the Digital Signature Standard. The DSA can be viewed as a variant of the El-Gamal signature scheme. Its security is based on the interactability of the discrete logarithm problem in prime order subgroups of ZP star. So, current draft version of FIPS 186-5 states, prior versions of this standard specified the DSA. This standard no longer approves DSA for digital signature generation. DSA may be used to verify signatures generated prior to the implementation date of this standard. See FIPS 186-4 for the specification for DSA. So actually, NIST standards no longer includes DSA. Okay? This is mainly because the security is here. Okay. This is why we always promoted or encourage people to use elliptic cryptography. Okay? But let's see how DSA works. You start with choosing a good hash function, like SHA-256 or SHA-3-256 or so. Then you choose key lengths, L and N. So for instance, if you want 128-bit security, then these numbers should be like this. Okay? Choose n-bit prime q, which is 256 bits in our example. Then you choose a larger prime, L-bit prime modulus p, such that p minus 1 is a multiple of q. Okay. Choose g, its multiplicator group order modulo p must be q. So now you generated some parameters, p, q, and g. So if you want to communicate, for instance, for 100 people, you can give these parameters to all of them and then start communicating, or you can choose new parameters for everybody you want to communicate. For instance, in Bitcoin or similar cryptocurrencies, here we use an elliptic curve instead of these groups. But that elliptic curve is fixed and everybody is using that. So we know the domain parameters. How the key generation work is similar to El-Gamal. You randomly choose a secret key X, okay? Then calculate G to the X mod P, so you obtain your public key. So when you want to sign something, you will use X. And when people want to verify your signature, they will use Y. This is the whole idea. So signings work like this. For every message, you randomly choose K. This is important. If you use the same K for two different messages, for signing two different messages, your secret key leaks. Okay? This is very, very important. This happened in Bitcoin, actually. There was a bug in Android Java random class. So people who use some wallets on this in which this wallet used this Java class. So that random number generator took the seed identical every time. So they produced the same random number. So people started to sign two different transactions, the same number K. And in a few hours, they lost all of their money because somebody captured their private key and transferred their money to some other address. So This is very, very important. So in every implementation, this is the part you need to check actually, if it is really random and if the same number is never used twice. So, but we were talking about signing. So you have a message M. To sign it, you choose a random parameter, which should be kept secret, of course, K. So you calculate G to the K modulo P modulo Q. This equals to some value R. Then you take your hash of your message, then add your secret key X here, okay, and multiply it with the inverse of this number. It equals to S, then you say that my signature is R and S, okay? Now everybody needs to verify this. So what they do is as follows, they take the S and calculate the inverse of it. Again, you can use extended Euclidean algorithm for these inverse operations. Since message is not secret because this is not an encryption algorithm, they know the message. So in cryptocurrencies, this is the transaction you sign. So they also calculate the hash of it, multiply it with this value, and they say that this is U1. Calculate R times W. R again comes from your signature. So as you can see, you are only using values from this signature. Okay? Then you calculate white power of U2. Y is the public key of the signer. So the verifier uses Y, the signer uses X. After these operations, you end up with this value Y, and the signature is valid if Y equals to R. This one. So if you just use pen and paper, you will see that by basic number theory, this actually holds if the signature is valid. Okay, so it is not that hard. But as you can see, if I replace this part with an elliptic curve, and instead of performing group operations, if I perform operations on the elliptic curve, then I will have elliptic curve digital signature algorithm. Okay, and this is what Bitcoin or any other similar cryptocurrency like Ethereum uses. Okay, for this reason, next we will talk about elliptic curve cryptography. So before moving on to elliptic curve cryptography, let's look at the security of DSA. The security of DSA relies on two different discrete logarithm problems. One is the discrete logarithm problem in ZP star, where the number field sieve algorithm applies. This algorithm has a sub-exponential running time like this. Okay? So it looks a little bit complicated, but the important thing is that we have a sub-exponential time algorithm for this, which is the number field sieve algorithm. So this is on ZP star. But for the generic group, the second discrete logarithm works to the base G in the subgroup of order Q in ZP star. Given P, Q, and G and Y, your aim is to find X such that this equals to this, right? For large P, for instance, 3072, the best known algorithm for this problem is Pollard's row method, which actually solves it in square root of Q. So this is not a big problem here. This is why we actually chose our, recall that we start with choosing two random, let me go back. Here we chose two key lengths, L and N. We choose N equals to 256 due to Pollard's row algorithm. We choose L equals to 3072 due to number field sieve method. Okay, so we can get rid of this part if we use elliptic curve cryptography. This is the main idea. Okay, so this is why security of this DSA is not as good as elliptic curve cryptography, and there are some other kinds of attacks for this kind of algorithm. So this is why NIST actually removed it from its standards.